And welcome to the final installment of the Chapter 9 series. And this one isn't really even in Chapter 9. It's kind of a standalone discussion because we're going to talk about Zener diodes. And if you've thumbed through your textbook, Boylestad does not spend any time on Zener diodes in this book because he leaves it for his electronic components books, I think. So that's where we're going to start here. And as you can see, I've got up here two different scenarios, and I've got the schematic symbol for the Zener diode. And so it kind of looks like a silicon diode. A silicon diode just has this structure, right? And then, from here to here, there's a 0.7 volt drop, okay? When Zener diodes, which have these little tails on the end of the bar, I forgot the bar here, that indicates that it is a Zener diode. Okay, when it's in forward bias, it's going to operate exactly like a silicon diode, right? It's going to drop 0.7 volts. When it's in reverse bias, however, it just depends on what the voltage is, because in both cases, if the current is moving that way, you can see that that's pointed with the current, and so it's in forward bias, and you can see that this one is pointed against it, and that's in reverse bias. See? So the Zener diode actually operates in this breakdown region. If we looked at the characteristic curve, so a typical diode does something like this, around 1 volt, 750 millivolts, somewhere around there, 700 millivolts, and typically it stays zero over here the whole time. With a Zener diode, depending on what it's rated for, in this case I have one 4.4 volts, so let's just stick with that. So in this case 4.4 volts, and so it actually will conduct in the opposite direction. And so that's really why you buy these, because that reverse bias voltage is what you're purchasing them for, okay, as opposed to just using any other component. So it almost kind of acts like a voltage regulator for different parts of the circuit. And if you have a cell phone or if you have a tablet, you've got something like this, right? That's a USB charge on the side, and this is not going to translate too close here for the focus, but if you look on the back there, this thing is regulated for 5 volt output typically, because that's what your phone is charged with. And so on the output terminals of that power supply, I guarantee you there are capacitors and there are Zener diodes, because they want to tightly regulate 5 volts on that output, okay? Because you don't want your phone, your super expensive $1,000 phone or whatever, to be over voltaged or over currented. So you want a nice, steady, regulated 5 volt controlled circuit, providing current to charge your battery. So these will always operate in the breakdown region. Like I said, you could use them this way, but silicon diodes are cheaper. You would probably just use a silicon diode. But we should be aware of this, and I'm going to do a couple of examples where I've got them in both configurations, okay? And like I say here, it comes in values from a few volts to 100 volts typically. So it's a static voltage regulator. You cannot change what the voltage output is. Okay, so you would have to know this before you buy it. All right, so let's go ahead and do a couple of these. And as I say up in the corner up here, it says treat it as a voltage source. And that it doesn't matter if it's in positive, or if it's in reverse bias or forward bias. Okay, same thing for any diodes, really. You could look at them all as voltage sources, but prior to Chapter 7, Chapter 8, we didn't know how to deal with those, right, if we had more than one voltage source. So let's go ahead and I will create a circuit here. So here we go. If you want to go ahead and take notes, jot this down. So we have a 9 volt source. We have a 300 ohm resistor in series with the source, and then we have this Zener diode. Note that it is in reverse bias mode, because we know that source is going to produce a current that way, this way, and this way, since there's only one source, right? So we know that this is in reverse bias. So it's going to act like a 4 volt source. So let's go ahead and redraw this, and you'll see how simple this makes the analysis. Okay. So there's my 4 volt source. Here's my other two resistors. and 400. So 300, 200, and 400. So I know what all the voltage drops are because this point right here, because there's no other resistance in series here, that changes if we put a resistor on this branch. But for right now, on this branch here, because this is how we typically use them, we're going to ignore any internal resistance that this Zener diode has. Okay, now you wouldn't do that in real life because, as I just stated, you know, you want to make this as accurate as possible, and so you would take that kind of stuff into account. So there is an inherent resistance internal to this, but we are going to assume that the resistance on the Zener diode is 0 ohms. Okay, and it doesn't change the analysis that much. It just makes it a little bit more difficult. You then have to go use Chapter 7, Chapter 8, Chapter 9 techniques. Okay, not Chapter 7, but Chapter 8 and Chapter 9 techniques. Okay, whereas if you just assume it's 0, this makes it a piece of cake. As I yank my microphone off here again, I am going to put a little thing up here on the wall. Hopefully I get that done soon. But anyway, we know that this point right here has to be 4 volts because there's a 4-volt source there. Just like we know that this point right here has to be 9 volts. And we are assuming that down here, right, that this is our 0 volts. So that means that we have a 5-volt drop from here to here, and we have a 4-volt drop across this branch. Okay? So let's go ahead and figure this out. What's the voltage across the 300 ohm? Well, it's just 9 minus 4. So 5 volts. And then the voltage on the 200 is going to be, well, 4 volts times 200 over 600, right? If we do our voltage division here. So this one over the total, and then we'll do this one over the total. So this is going to give us 1.33 volts, because that's 1/3 of 4. And then the voltage on the 400, 4 volts times, now this time it's 400 over 600. So 2/3 of 4, which is, 2.67 volts. Okay, I think that's what I said. Yeah, 2.67 volts. Okay, so in either case, we could find the current through there, but we could also find this total current as well. So, if we want to find the, if I erase these real quick, so we have, I'll do the voltage drops on this one. So the 300 is a 5-volt drop. The 200 is 1.33 volt drop, and for the 400 we've got 2.67 volts. Okay, now I can erase what's on the bottom here, and now I want to find the currents. Okay, so I've got the current through the 300, which is really the source current because it's in series with the source, so that's 5 volts divided by 300 ohms. Remember, the current through any resistor in any position anywhere is the voltage divided by its resistance. So 5 volts divided by 300. And I get 16.7 milliamps. So that's what my total is. 16.7 milliamps. Now let's find that branch current, and I could use, I'm just going to use the total voltage across that, which is, so this is through the 200, which is the same thing as the current through the 400 because they're in series with each other on that branch. So I've got 5 volts, whoops, not 5 volts, I've got 4 volts. I've got 4 volts divided by a total of 600 ohms. And that gives me 6.67 milliamps. So that means essentially 10 milliamps is coming this way because I just take the difference because KCL. So 6.67 milliamps, that's really the only way you could find this. Otherwise, if you knew what that internal resistance was and you found what little voltage drop it had, then you could accurately calculate what that current would be, okay? But in this case, we don't have to worry about it. So we just subtract the two because otherwise you can't there is no resistance technically here because it's a source. So the current is still going to move through the source in the other direction. It's just that, we just take the difference of the two, and now we have this. Okay? All right, so let's see if Multisim agrees with what we just did. All right, so I've got both of these circuits hooked up now, and I wanted to wait to show you how to add the Zener diode and what I would do for this. So I'm going to go up to Place, Component, go to Group, Diodes, Virtual, Zener. Make sure you go to Virtual, otherwise you have to pick an actual component with the actual model number. It's got hundreds or probably thousands of them in here. So you want to go to Diodes Virtual Zener, then you can make it whatever you want. So I'm just going to make it right here, close. I'm going to add this in, and I'm going to just double click it, and I want this to be a breakdown voltage of 4 volts because that's what we did. Okay. And so let's see here. I'm going to go ahead and go ahead and simulate this. Put a voltage probe in. Put a voltage probe in here, and a voltage probe in here. Okay, so we know that those agree, so that's a good sign, which we would expect, right? So now I'm going to right click this, reverse probe direction, 16.7 milliamps and 16.7 milliamps. Now let's go find the current on this branch out here, 7.97. What did we say? We said 6.67. Oh, that one's 300 ohms. Quick change. I'll leave this in. I'm not going to reshoot the whole thing. I bet you caught it before I did. Let's try this again. There we go. So notice it had almost no effect on this total current available, right? Because this regulates how much voltage is there. Whatever current gets passed through, you can fine tune that, but for this one, it's regulating it at 4 volts, and that means that this has to be a 16.7 milliamp total current. So here we go. There it is, 6.64 milliamps. Now let's go find this branch current, and there we go. Okay, and I guess the last thing to find would be the total current here, or I'm sorry, the current through the diode here is 10.1 milliamps, and then we should have the same thing here, 10 milliamps. Okay, so it looks like we did it correct. All right, so this time we're going to look at one with a reverse bias and a forward bias. And you can see here, all I've done is essentially I took that other problem and I replaced that resistor with a forward bias diode here. So, So here we go. Next one we're going to look at, I essentially just replaced this resistor with a forward bias Zener diode. It's essentially the same setup here, but same thing. The source this source is going to produce a current. It's going to split this way, and this one is pointing in line with the current, so this one's going to drop 700 millivolts. And we will say that the voltage of the Zener here is, let's call it 5.5 volts. Okay, so that means that this one is going to be a 5.5 volt battery or DC source. So let's go ahead and rewrite this. So I keep my 25 volts and my 1.2 k ohm resistor. This I'm looking at as if it were a, remember, if you have a voltage drop, draw it as this. Okay, so this is positive to negative, so this is reverse bias. So this is whatever it's rated for. Okay, in this configuration with the polarity. The polarity is always going to be positive to negative voltage drop in the circuit. Even for this one, we're going to use, instead of the 5.5 volt, that one's going to be a 0.7 volt or 700 millivolt. Okay, so this is 5.5 volts. And this one, we're going to look at as a 0.7 volt drop. And this is the 2.2K. All right, well, we know what this voltage is right here. That's 5.5 volts. So if we do all of our voltage drops, we've got the voltage of the 1.K is 25 volts minus 5.5 volts, which gives us 19.5. And really the only one we need to find is the 2.2K, right? Because that's the only other resistor we have. So in this case, there's 5.5 volts on this side. There's a positive 0.7 volts node voltage right here because that's a source, so that has to be what that node voltage is right there. That gives me 5.5 volts minus 0.7 volts, which is what, 4.8? Okay. All right, so let's put those numbers here. So this is 19.5 volts. That's going to produce a fairly big current. And we've got 5.5 volt drop across here. And then this resistor has a 4.8 volt drop because this one has to drop 0.7. All right, so now let's find the currents. Again, I can just use Ohm's law. So let's do that this time. So just in both cases, because I don't have voltage division to do over here, I can just say the current through the 1.2K is 19.5 volts divided by 1.2K, and the current through the 2.2K is, what did we say? We said it was a 4.8 volt drop, so 4.8 volts divided by 2.2K. So let's see what these are. So first up, 19.5 divided by, 19.5 divided by 1200, and I get 16.3, so that's rounded up. 16.3, so we might be like 100 microamps off of multisim. We'll see. The next one, 4.8 divided by 2200, and that gives us 2.18 milliamps, which means 16. We'll call it 16.1, right? That's essentially what it is. So the current through the Zener, 16.1 milliamps. And all I did there was take this one minus this one because that's what's coming into the node up here. That is the 16.1 milliamps. And then over here we have the 2.18, which means, that's 2.18 milliamps. That's 14.1. I bet you caught that one too. So that's 2.8. So that means it's 16.3, right? 16.3. 2.18, so that should be 14.1 down. Milliamps down, and then, yeah, there we go. I said 16.3. Yes, it's 16.3, and then 14.1 through the Zener. Okay. Well, that was pretty straightforward. Let's see if multisim agrees. All right, and here we go. I've got the circuit recreated here, and I do need to change the voltage source, and this is 25 volts, and this is 25 volts. This is using a 5.5 volt Zener diode in both cases, but we know that in this direction here, or let's see here, this is also a 5.5 volt, but notice that it's in forward bias here, okay? So let's go ahead and put a couple probes in here. Voltage probe here. Voltage probe here, play. Okay, so it looks like we have 5.5 volts there. That's good. That's a good start. Let's see what the current is here, 16.3. Let's see what the current is here, 16.3. So I'm pretty sure we figured out that this was 19.5 volts across this 1.2K. That looks to be correct. Let's go ahead and add some more in here. There's our, we expected 2.18 milliamps, and then we have 2.24 milliamps. I said we'd be just a touch off because of how we had to round up that one number, the 16.3, okay? So let's go down here and see if we have the same thing. Okay, so now that matches more closely what we have here. So my guess is that if we were to open this and look at the properties, let's see. See, it says a forward emission coefficient of 1, but see, I'm not sure exactly what that means. So they're probably doing something very, very similar, but I wouldn't squabble over that. That's essentially the same thing here. Okay, so let's look at the current through the Zener. Turn it back on. So we get 14 there, and we've got 14.1 here. Okay, so this actually aligned exactly with how we did our problem, right? So that's what we would expect here. And here it's doing something that's just a tiny bit different in terms of this right here. So there may be some tiny resistance that it's taken into account too. I'm not sure because it does say 5.49 volts. But anyway, looks like everything is happy and agrees. And thank you for watching.